So this is switching and routing chapter number 2. So for this module, we are going to be introducing ourselves to the switching concepts and how switches generally work. Of course, we'll be explaining the forwarding process of a switch, comparing of collision domains to broadcast domains, and so forth. Now, when you are having devices on a switch, when you're having devices on a switch, that is PCs, they will be exchanging information with each other. The process that is the definition of the term that enables a switch to move data from one computer on one port to another computer on a second port is called forwarding. The data type that's being exchanged are called frames, and these frames are normally forwarded from one port to another. On one port we'll have the source device, and another port will have the destination device. So, two terms associated with frames entering or leaving an interface on a switch are ingress, which means entering an interface, and egress, meaning exiting an interface. So at ingress, you normally find the sender of the data moving from the computer to the switch, entering the switch. And then at the destination, it will be exiting the switch, that is egress, to the destination systems. So for example, in this case, you could have a PC on port number 1 and a PC on port number 6. When the PC on port number 1 sends data will move from the PC to port number 1. So port number 1 will be the ingress interface. As it's being delivered at destination on port number 6, it will exit out of port 6 and get to the destination, that is egress. So a switch forwards based on the ingress interface and the destination MAC address. And a switch uses what they call a MAC address table to make those forwarding decisions. A switch will never allow traffic to be forwarded out of the interface it received the traffic. So when a switch is receiving traffic from computer number 1, it will never send that same traffic back onto the port where computer number 1 is located. Let me repeat it again. If we have a PC on port 1 and it is sending out data, the switch will never send that data again back onto the same port. It can send them on all other ports apart from the port where the data came from. So a switch will keep what they call a MAC address table, and that MAC address table helps it keep track of which computers are on which ports. So a switch will use the destination MAC address to determine the egress interface. Before a switch can make a decision, it must learn what interface the destination is located. A switch builds a MAC address table, also known as a content addressable memory table or CAM table, by recording the source MAC address into the table along with the port it was received. So I want to demonstrate this part practically by going to my packet tracer. So here I have my packet tracer. I am going to introduce a switch, 960 as usual, and then three computers. Now, I am going to connect these computers to the switch. I will zoom it a bit, make it a bit bigger. So you notice here we have our three computers. Now I am going to give these computers IP addresses. I'll begin with this one here. I'll give it the IP 192.168.2.1. Subnet mask automatically puts itself there. Then I'll go to the second computer. The second computer also, I'll give it an IP address. Then I'll also issue the third computer. So please note that I'm giving them IP addresses from the same network. The first three parts of the address are the same. Okay, so if I pass my cursor over them, you will see that this is 2.1, 2.2, and 2.3. Now, a switch keeps what they call a MAC address table. The MAC address table keeps the MAC addresses of each of these devices and associates them with the port on which they are connected on the switch. So how do we know the MAC address? First of all, I run my command ipconfig or. So this here is my MAC address. It's also called the physical address. Okay, remember it ends with 9EA AA for that PC number 0. I go to the second PC, ipconfig or. This ends with D295, and then lastly I check this other one here. Sorry, ipconfig or. It ends with 5A 5D. Now, when this PC wants to communicate with this PC, the switch does what they call forwarding. It receives the data on this port where this PC is located and then forwards it to the port where this other system is located. How does it do it? It uses what they call the MAC address table. So let me start by testing my connectivity. I'll say ping 192. Remember, this PC is 2.1 as you see, so I'll ping the others. And I also ping 2.3, the third PC. Then now I want to check with the switch, how has it been able to do this? How was the frame forwarding able to happen? So I open up my switch, I check out the command line interface, and I use a special command called show MAC address table. As you see here, the switch has built a MAC address table. It has gotten every PC and its port on which it connects and done what they call learning. Now, whenever a PC is sending data to another PC, the switch will record the MAC address of the sending PC onto the port where that PC is located. So as you see here, we have a MAC address ending with D295. Okay, D295 is on fast Ethernet 0/1. So let's look at it and let's look for it among the actual PCs. So I go to this PC here and say ipconfig all. This is not the one. I go to this here, ipconfig all. It is here, D295. So let me compare here with my command prompt here. So we see that these ports, over here, if you look at them side by side, you are able to view in this output that this, a bit here, you're able to view from this output that the MAC address of this PC, first of all, is that there ending with the D295. And if you compare here D295, it means that this PC number 1 is on port 1. Okay, how do I verify it? Let me look at it physically. If I pass my cursor here, as you see, it's on fast Ethernet 0/1. So how has it been able to do this? As the PCs were exchanging data, the switch recorded the MAC address of the sending device onto the port where that device is connected to. So that means that for PC number 2, it will record its MAC address onto fast Ethernet 0/2. For PC number 1, it will record its MAC address on fast Ethernet 0/1. For PC number 0, it will record its MAC address on fast Ethernet 0/14. So in case this PC wants to communicate with other PC, the frame comes to the switch. The switch will look at the destination MAC address. Where is the destination located? And when it finds the MAC address of the destination, it compares that value with the information it has in its MAC address table. If it sees that the MAC address matches with port number fast Ethernet 2, the destination part of the MAC of the frame matches with, the destination MAC address of a frame matches with an entry in its MAC address table, it sends it to the port where that device is located. That's what they call the frame forwarding. So a switch will use the destination MAC address to determine the egress interface before a switch can make a decision, and it must learn what interface destination is located. A switch will build what they call a MAC address table, which I've just shown you, also known as the content necessary memory table, by recording the source address into the table along with the port where it was received. And that mapping is what the switch bases its forwarding on. A frame comes into the switch, it checks this table and knows which destination, where the destination is, which port to send it to, where the destination is located. So a switch will use a two-step process when it is before forwarding the frames. Step 1 is to learn. It examines the source address and adds it to the MAC address table if it is not there. It then resets the timeout, setting back to 5 minutes if the source is in the table. Then after learning the source, it then does forwarding. If the destination MAC address is in the MAC address table, it is forwarded out on a specified port. If the destination MAC address is not in the table, it floods out on all the ports apart from all the ports the port was received on. So it tries to find the destination by flooding out onto all the ports. And normally in this case, if a PC receives a frame whereby its address is in the destination part, it will process it and reply the sender. So within your notes, you have a video that covers how a switch builds a MAC address table. I've just demonstrated in Packet Tracer, and how they forward the frames. Switches use software on applications specific integrated circuits to make the quick decisions. A switch will use 1 or 2 methods to make forwarding decision after it has received the frame. Now there are 2 methods the switch will use after it has determined where to send the frame before sending it, that forwarding process. The first one is store and forward switching. In this case, it receives the entire frame and ensures the frame is valid. Store and forward is the Cisco preferred switching method. It stores the frame first, says if the frame is valid, and then transmits it. So this ensures that invalid frames or error frames are not sent across a network. It cleans up your network for you. Then we have the cut-through switching. Cut-through switching, it forwards the frame immediately after determining the destination MAC address of an incoming frame or determining which port is the egress port. This one doesn't do any checks. It doesn't check if the frame is valid or not. It just simply receives it and sends it out to the destination. How does store and forward work? Store and forward has 2 primary characteristics. Because it has to store the frame first, it is able to do error checking. The switch will check for the frame check sequence for cyclic redundancy check errors, and bad frames will be discarded. So with store and forward, which is the Cisco default way of forwarding frames, that's why Cisco switches are efficient, is that they will not forward frames which have errors in them. And then it also does what they call buffering. The ingress interface will buffer a frame until it checks the frame check sequence. This allows a switch to adjust to the potential difference in speeds between ingress and egress ports. Now, what buffering means is that the interface where a frame has been received, it has a storage there to keep all frames that are going to be checked. And the benefit of this is that sometimes the destination device may be slow. By buffering, it's able to deal with the competing speeds. For example, many of us go to the internet and are watching a movie. But sometimes the movie won't download and won't be able to be viewed in the speed that we want. So most of the applications will use fast buffer, meaning that they first accumulate a bit of the movie and then begin playing it. that it can play continuously. So instead of the movie fading to play, it first loads for some time. After it has reached a specific threshold, the movie begins playing. Okay, so it's a way to adjust between two competing speeds. On the internet, normally Uselink may be very slow, yet you want to play the video very fast. So YouTube will do things like buffering, whereby it downloads bits and pieces of the download, so it can begin playing with you for you while it continues downloading. So it's there to enable difference in speeds. Now on the switch, the data type being exchanged is basically a frame, and a frame has a number of sections. It has the header, the frame header, the network header, transport header, and the actual data. So within the frame header of a frame, you will find the preamble, destination MAC address, source MAC address, and the type. And at the trailer of the frame, we will find what they call the checksum or the frame check sequence. This area is used for testing for errors and confirming that these frames are valid. Okay. Then we have another type of switching called cut-through switching. Cut-through switching forwards the frame immediately after determining the destination MAC address. Now with cut-through switching, it won't check for errors. So it means that with cut-through switching, even invalid frames will be sent because for it just checks for the destination and that's all. However, it has a variant called fragment-free. The fragment-free method only checks the destination, but also checks to ensure that a frame is at least 64 bytes. Now, frames have minimum and maximum sizes. The minimum size of a frame is 64 bytes, and the maximum is about 1,500 bytes. So in this case here, cut-through switching, which is called frag-free, it is there to ensure that no frames that are lower than 64 bytes are transmitted. Because normally, those frames that are less than 64 bytes are results of collisions and therefore are called fragments or runs. So the concepts of cut-through switching are normally very clear. It is appropriate in scenarios whereby you don't want any delay. Of course, cut-through switching is very fast because there are no checks being done. Okay, and there won't be retransmissions. So store and forward is used in scenarios whereby you don't want any errors on the network, by all means. But then cut-through is used in situations whereby you want little or no delay. Okay, so cut-through switching won't check for errors, meaning that it will change packets that are invalid. It may also lead to bandwidth issues because the switch may be overwhelmed with so much traffic, of which most traffic is invalid. But Cisco switches clean this up for you because for them, they check every frame as it comes in for errors. Then also, the problem with cut-through switching is that it cannot allow for communication between ports of differing speeds. So generally, a Cisco switch can communicate with another switch. A Cisco gigabyte switch can communicate with another switch which is 10 Mbps because it supports store and forward. With store and forward, it's able to do what they call buffering. Some frames can be kept, can be stored in the meantime, and then transferred at a manageable rate for a slower device because there is a storage where those frames can be stored in the meantime before transmission, which enables two ports to work together, a fast port and a slower port, because there is a storage where frames first go to enable the switch to adapt, the ports to adapt to different speeds. With cut-through switching, it can't happen because as it receives is the same rate it sends, meaning that if you have a slow port will be overwhelmed by the faster port because there's no mechanism by which the transmission can be slowed, for example, through storage. So for that case, it will never support ports that are running at differing speeds, going from ingress to egress, that is in and out. Now, switches eliminate collision domains and reduce congestion. When there is a full duplex on a link, a collision domain is eliminated. Collision domains are created in situations whereby we have half duplex, whereby you can only send or receive at a time. But switches are full duplex, and for that reason, they eliminate collision domains because of working in full duplex. When there's a full duplex, all collisions are eliminated. When there's one or more devices in a half duplex environment, there will be a collision domain. And in case of a half duplex scenario, there will be contention for the bandwidth and collision will be possible. Most devices, including Cisco, use what they call auto-negotiation. And this enables the system to automatically set the duplex speed, the duplex and the speed of the ports. So auto negotiation, Cisco devices are able to detect the settings of the device attached to them. If it's a 10 Mbps device, they adjust to 10 Mbps. If it is half duplex, they adjust to half. So Cisco switches are normally very intelligent because they support things like auto negotiation. Then we have what they call broadcast domains. Switches extend broadcast domains. They reduce collision domains because they are full duplex, but then they expand broadcast domains. A broadcast domain extends across all layer 1 and layer 2 devices in a LAN. The only device that breaks down a broadcast domain is a router. Okay, so the only a layer 3 device or a router will break down a broadcast domain. The broadcast domain consists of all devices on the local area network that will receive the broadcast traffic. When a layer 2 switch receives a broadcast, it will flood it out on all the interfaces apart from the interface where that message was received, or the ingress interface. Too many broadcasts will cause congestion and may lead to poor network performance because they create a lot of traffic, which leads to reduction of bandwidth, which reduces the performance. Increasing devices at layer 1 or layer 2 will cause the broadcast domain to expand. The more switches you add, as you see here in the diagram, the bigger the broadcast domain. The more switches you add, so to break a broadcast domain, you have to introduce a router to create separate networks. So switches will use a MAC address table and full duplex to eliminate collision domains and avoid congestion. So some of the features that are used to avoid congestion on switches are fast port speeds. Depending on the model, switches can have up to 100 gigabits per second in port speeds. Fast internal switches. This uses the fast internal bus or shared memory to improve performance. So some switches have an internal bus that enables switches, especially layer 3 switches. Large frame buffers. Buffers, remember, are where frames are first stored before they are sent out to the egress ports. So some switches have large frame buffers to allow for temporary storage and processing of large quantities of frames to improve congestion. And high port density. This provides for many ports for devices connected across the LAN with least cost, and also provides for more local traffic with less congestion. So Cisco switches support high density. Now we have so many models of Cisco switches. Some are 24 port, some are 48 port, some are 56 port, some are modular and can be made in form of a rack. So the more the ports, the more the less congestion that will be in the switch. You come across 48 port switches, 96 port switches, 100 port switches. So there are so many ports switches you'll find, all with different port densities, some with more ports than others. And that's all for this chapter. It's all about how switching actually occurs.